Okay, so the question is, how do you solve an equation if the variable, in these cases the variable is x, begins the equation underneath a radical sign? So I've kind of set up three different examples here, and the basic principle that we're going to use to solve each of these examples is the same, but you'll see the kind of equations that we end up ultimately solving are a little bit different in each case. But the key idea behind how to deal with a variable that is sort of trapped underneath a radical is the same every time. And that key idea is that a square root is the opposite operation to squaring a number, right? The square root of 100 is 10 because 10 squared is equal to 100. And therefore, if you have a square root in an equation, what we'd like to do is we'd like to square it away. In other words, we'd like to raise both sides of the equation to the power 2. If we can do that, then chances are that that square root is likely to go away. The only problem with this, and it's not a problem that's going to show up in any of these examples, but something to be careful about in general, is I can only do this if my square root resides over the entirety of either the left side or the right side of the equation. If it only exists over one term, let's say I'm doing square root of x plus 5 is equal to 12 or something like that. It would do me no good in this example to square both sides, because if I were to square both sides, I would have to square the binomial on the left-hand side as well as the 12 on the right-hand side. And then I would end up having to FOIL this out. And when I FOIL it out, I'm going to get a cross term. The outer and inner terms are still going to have square root factors in them. And so I don't want to use the square both sides directly in this example. It's too soon. So instead, if I did have an equation like this, I'd want to get that square root by itself first before I tried to square both sides. So in this example, I would start by subtracting 5 from both sides, and then give me the square root of x is equal to 7. And then I can square both sides. And when I square that square root of x on the left-hand side, that's exactly what cancels the radical and leaves me on the right-hand side with 7 squared, which we would call 49. So that's just a bit of a cautionary warning before we launch into these examples, that all these examples are already sort of set up to do this, but we can only use this technique when the square root is over the entirety of one side or the other, is over the whole side of the equation and not just over an isolated term. So each one of these examples over here on the right is already set up to do that. And so our first step in these problems is going to be to square both sides to get the ball rolling. So in our first example here, let's call it example 1. We've got a radical expression on the left-hand side. We have just a number on the right-hand side, 7. And so the first thing I'm going to do is I'm going to square both sides. Just raise both sides of this equation to the power 2. So over here on the left, raise that to the power 2. Over on the right, I'll raise that to the power 2. And again, the entire purpose of doing that is that that square on the left and that radical with an index of 2, in other words, the square root, those are going to cancel one another out, which was the entire point. What we're trying to do here is to cancel out that radical so that I can get just 2x minus 1 in this example on the left-hand side. And on the right-hand side, 7 squared is 49. So that squaring both sides step is the crucial step. And we could do it right away here because, again, the entire left-hand side of this equation was underneath the square root. And from here, it's just a matter of unwrapping the variable using the reverse order of operations. Addition and subtraction happen first when you're trying to unwrap a variable. So we'll add 1 to both sides, end up with 2x is equal to 50. And then multiplication and division happen afterwards when you're using the reverse order of operations. So we'll divide by 2 on both sides and end up with a solution, x equals 25. So our first step in this example was to square both sides. And the reason we do that is because squaring is the opposite of taking a square root. And so when I square both sides, that radical, that square root on the left-hand side, disappears. Very same thing is going to happen in the second example here. Just because there are radicals on both sides doesn't make our strategy any different. If I go in and I square both sides of this equation, then the same thing is going to happen. Every radical that I square is just going to vanish. And that will, in this example, take care of both the radical on the left and the radical on the right, which are preventing us from solving these equations the way that we want to. So I'll come in here, I'll raise the left-hand side to the power 2, I'll raise the right-hand side to the power 2. And again, the entire purpose of that is for what happens next. That second power and that radical with an index of 2 are opposites. They're inverse operations to one another, and therefore they cancel one another out. And so when all of that dust settles, the only thing we have left in this problem is x minus 3 on the left-hand side and 3x plus 1 on the right-hand side. Okay, cool. So now we have an equation that is just a linear equation. It involves only first powers of x on the left and the right-hand sides. So now we know how to solve this. Since we have x's on both sides of the equation, the first thing we should do is fix that by subtracting all of the variable terms onto one side of the equation. And while we're at it, I'll do this one step at a time here. 3x minus x is going to give me 2x. I still have a plus 1. I still have minus 3 going on this side. And now, again, reversing the order of operations requires us to finish our adding and subtracting first. If I subtract 1 from both sides, I'll get negative 4 is equal to 2x. And then I can do my multiplication and division. Divide by 2 on the left and the right. And I'll get negative 2 is equal to x. And so there is what looks like a solution to this problem. I do want to use this example, though, to illustrate a secret problem, a secret minefield that can happen when you're solving equations involving radicals. This, by the way, is also a really good practice no matter what kind of equations you're trying to solve, and that is check your answer. Plug your value of x back into the original equation just to be sure that you got the right answer. If I do that in this example, plugging a negative 2 in for x, so negative 2 underneath the radical here, minus 3 square root, is supposedly at least equal to the square root of 3 times negative 2 plus 1. So if I go in to check this, I'll do all the arithmetic underneath these radicals. Square root of negative 2 minus 3 is going to be the square root of negative 5. And on the right-hand side, 3 times negative 2, that's negative 6, plus 1 is also negative 5. But here's a problem. What is the square root of negative 5? Not only is it not a whole number, because 5 is not a perfect square, it's not even a real number, because negative 5 is not non-negative, right? Negative 5, being a negative number, does not have a real square root. So whether or not the x equals negative 2 actually is a solution of this equation kind of depends on what kind of numbers we're allowed to work with. This is actually a bit of an issue for us. It's not that I would take off points on this on a final exam in our course, but in another course they might. What this suggests to us is that x equals negative 2 really isn't a solution to this equation, unless we permit both sides of this equation to take non-real values. So that's just something weird that can happen when you solve radical equations the way that we're solving them here. There really is no other way to solve this equation to get a value for x other than the way that we approached it. But really, when we try to do that in this example, there is just not a way to get these two things to match up. Maybe in a moment, we'll take a look at the graphs of the two expressions, y equals the square root of x minus 3 and y equals the square root of 3x plus 1. And maybe we'll be able to convince ourselves of why this equation has no solution by looking at the graphs. So I want to do that before we move on to another example. But I want to finish on this screen, at least, by working our third problem, in which we have a variable expression on one side which is not under a radical, and on the right-hand side which is under a radical. But again, our strategy is completely the same. To get rid of that radical, again, because it applies to the entirety of the right-hand side, we're just going to square both sides. By the way, this is an example that is completely analogous to the example that's already in our YouTube playlist. So if you check in our YouTube playlist on objective number 41, you'll see an example that's just like this. So the square on the right-hand side is going to knock out that radical and leave me with just x plus 10. But then the thing to be careful about is on the left-hand side, we have the square of a binomial. We have the quantity x minus 2 squared. And because it's a binomial, because we have subtraction going on inside the parentheses, what we can't do is we can't distribute that power. We have to rewrite it and multiply it out using the distributive property of multiplication over addition, better known as FOIL. So we could and should change that square into a multiplication, use the FOIL technique to multiply everything out. Here I'm going to end up with x squared minus 2x plus 2 times 2. And then on the right-hand side, I'll have x plus 10. Okay, great. So now we've simplified the left-hand side and the right-hand side. But I have x's on both sides, and so I should fix that by subtracting to move x's from one side to the other. I'm going to subtract the x from the right-hand side to move it to the left. I'm going to also subtract the 10 from both sides. In doing so, I'm going to end up with an expression on the left, x squared minus 4x minus x is going to give me minus 5x, plus 4 minus 10 is going to give me minus 6. And on the right-hand side, I'll have 0. And now I have a quadratic equation that's in its standard form, ax squared plus bx plus c, and I have a 0 on the right-hand side. That means that this is a perfect case of a problem that we would want to try to factor. And to factor the expression on the left-hand side, we can factor it into a product of binomials whose first term is x, and whose second terms are whole numbers, or integers, I should say, which multiply together to give us negative 6, and which add together to give us negative 5. And a few moments of quiet reflection should be enough to convince us that negative 6 and positive 1 fit that description. And therefore, because I have a 0 on the right-hand side and a factored expression on the left-hand side, I can split this equation into two equations. X minus 6 is equal to 0, and x plus 1 is equal to 0, using the famous zero factor property that says if we multiply two things and it gives us 0, then one of those things must have been 0 itself. So to finish solving for x, I need to add 6 to both sides of the equation on the left. I need to subtract 1 from both sides of the equation on the right. I'll get x equals 6 from my first equation and x equals negative 1 from my second equation. And of course, we should probably plug those back into the original equation to verify that they still work. I'm going to leave that exercise to the reader. It turns out in this example that that is, in fact, the case. So these examples all illustrate how to solve an equation where the variable is underneath a radical. And the key to all of it is as long as an entire side of the equation resides underneath that square root, then the first move should be to square both sides of the equation. Just raise both sides of the equation to the power 2, because that is going to erase the radical. And then you just have to chase through the consequences of that squaring. The most complicated example here where we had consequences to that squaring was over here, where I squared x minus 2 on the left-hand side. I needed to remember that FOIL was necessary. Otherwise, the equations that we got after squaring both sides were really not that tricky to solve. It was only in the example on the far right that it ended up being even quadratic. The examples on the left both gave us really nice linear equations that we could just solve by reversing the order of operations.